Hello, I am Ehsan Jafari, an expert in membrane technology. Before we start learning this lecture, just a quick note. I am available for your private consulting, system design, troubleshooting, and procurement. If you need professional support for your business, just hit me up on WhatsApp. Now let's begin the tutorial.
Hello everybody and welcome to this presentation. In the previous section, I explained the ROSA software tutorial and some guidelines for designing a reverse osmosis system for brackish water and seawater desalination. In this lecture, I'm going to present an example as designing a reverse osmosis system for brackish surface water using ROSA software. In this example, as you can see, the feed source is brackish surface supply water with STI less than 5. The feed water TDS is 1290 ppm, required permeate flow 132 gallon per minute, recovery 70%, and the required permeate quality is the permeate with TDS less than 50 ppm. In this slide, you can see the water analyzed for this example, including barium, boron, fluoride, chloride, calcium, potassium, magnesium, sodium, nitrate, aluminium, sulfate, carbonate, bicarbonate, silica, and strontium. Now let's getting back to the software and start designing this example. In the software, at first, I want to input some information about the project. The project name is Brackish Water, for example, BW, and STI less than 5, and TDS 1290 ppm. We have only one case analyzed by my name and company name IWRS. The unit is in gallon per minute in psi. I want to select this, and temperature in Celsius. Now I want to input the data in the feed water data page. At first I have to select the water type. As you know, the water type in this example is surface supply with STI less than 5. Then I have to input the data in this table. For this, I have to click on the specify individual solids and input the data respectively. Barium is 0.14, boron 0.153, fluoride 0.5, chloride 34.29, calcium 9.55, potassium 0.97, magnesium 7.2, sodium 328, nitrate 2.6, aluminium 0.001, sulfate 15.8, carbonate 0.22, bicarbonate 871, silica 15, and strontium 10. As you can see, TDS is around the TDS as presented in the example, but we have more anion, and we have to click adjust anion. Now the balance is 0, and the TDS is the same with the TDS as presented in the example. We don't need to work with a scaling information page, just go to the system configuration and start working in this page. But before designing with ROSA, we have to calculate the number of elements, the number of stages, and so on. That's why I want to go back to the slides and discuss about it. Let's review again the example. The feed source is surface water with STI less than 5. Feed water TDS is 1290 ppm. Required permeate flow is 132 gallon per minute. Recovery 75%, and permeate quality is TDS less than 50 ppm. If you look at this guideline from the previous lecture, we can select the element diameter according to the flow volume in liter per hour. In our example, as you can see, the system capacity is 132 gallon per minute, that is equal to 29.97 cubic meter per hour, that is bigger than 2.3 cubic meter per hour. That's why we can select an element with 8-inch diameter. According to the TDS in our example, that is 1290 mg per liter, the element with TDS less than 10,000 mg per liter can be selected. Accordingly, BW30 and LE element can be suitable for our case. Now the type of the elements and element diameter determined. To calculate the number of the elements, we need design flux. For this, you have to look at this table. According to the feed source, that in our case is surface water with STI less than 5, the design flux between 12 to 16 is suitable. To reduce the cost, I consider 15 as design flux for this case. You can also download the component of this table from the website in the lecture 18. According to this table and these parameters, we can select the active membrane area with 365, 370, or 400 or 440 square foot elements. For this example, I consider 365 or 400 to calculate and compare them, that which one can be selected in our case. Now you can calculate the number of elements according to this equation, as we have already discussed in the reverse osmosis design in 10 steps. Since design flux is in gallon per day, the permeate flow in our example is in gallon per minute, and that's why you have to convert it to the gallon per day. That's why I multiply this number to 1440 gallon per day to convert it in gallon per day. At first, I considered 365 square foot as active membrane area, and as you can see, the number of elements in this case is 35. To calculate the number of pressure vessel, I consider a pressure vessel with 6 elements, and that's why 6 pressure vessel has calculated in this case. Now we have to correct the calculation of the number of elements according to the number of pressure vessel again. And as you can see, 36 pressure vessel considered for this case. As recovery in our example is 75% and the feed source is brackish water, according to this table, the recovery is between 70 to 80. And that's why the number of stages can be 2 and the number of serial element position is 12. As we have already discussed, the staging ratio for the brackish water is 2:1, and that's where 4 pressure vessels in the first stage and 2 pressure vessels in the second stage can be considered. Now let's getting back to the software and design it with ROSA. Now I want to simulate it with the software. The permeate flow in our case is 132. At first you have to cross specify and then change it. Recovery is 75%, but feed flow has to be uncrossed. Recalculate and accept change and close. The stages in our case is we have 2 stages. For the flow factor, as TDS in our case is 1290, is not low, not so high, and that's why I consider 95 in this case. The element type is BW 365. The pressure vessel for the first stage is 4 with 6 element, and for the second stage is 2 with 6 element. Now I entered the number for the recovery and feed flow. I selected the number of the stages, flow factor, and I consider 25 for the temperature. We selected the type of the elements, BW30 365, number of the pressure vessel, number of the element for first and second stage. Now I can run this simulation. If you look at the report, we have a design warning. The warning is maximum element recovery has been exceeded. Please change your system design to reduce the element recoveries. Our product is BW30 365 and the recovery limit for this element is 50%. As you can see, the information for the stage 1 and stage 2 presented here in this report. For example, for the stage 1, the number of the element in a pressure vessel, we have 6 elements, 1, 2, 3, 4, 5, 6. And you have the information for each of which element for the stage 1 and stage 2, such as number of elements, recovery, permeate flow, permeate TDS, feed flow, feed TDS, and feed pressure. The error is related to the last element. As you can see, the recovery for the last element is 0.15. That is equal with the recovery limit in the design warning. But I think that was a little more. For example, maybe that was 0.151234 or rounded to 0.15. Now we have to reduce the recovery for this element to solve this warning. The design warning is for the first stage. It means that the first stage has overworked and we have to reduce the work for the first stage. To solve this, we have some way. One of the solutions is to create a back pressure in the permeate site for the first stage. It can reduce the recovery for this stage. Another way is to create a boost pressure for the second stage. It can also help for the first stage to reduce the work. At first, I want to create a back pressure in the permeate site for the first stage. For this, I have to create a pressure. I want to, for example, 7. As you can see, for both stages, we have the same back pressure. To solve this reason, as I have already told you, we have to uncross the same back pressure for all stages. And now we have a back pressure only for the first stage. Now I want to get a report. In this report, as you can see, we have again the same problem. Now I have to apply for the second solution. Now I want to apply a boost pressure for the second stage. And for this, for example, I want input 10 psi, and as you can see, a boost pressure created for the second stage that helped to the first stage. Now I get the report again. Now as you can see, the problem solved and design warning is none. TDS for the permeate is also 21.93, that is less than 50 ppm. Recovery for the elements also reduced. It means that the booster pump in the second stage helps to the first stage to reduce the recovery, and all the parameters also are in the required limit. The feed pressure also for this design is 162.81 psi gauge. It means that if you want to use BW30 365 element, you have to apply 162.81 psi gauge to produce this permeate with this condition. Now I want to continue the design with the next element, LE400. As you can see, the number of the elements reduced because the membrane area increased. The previous membrane area was 365 square foot. In this element, we have 400 square foot, and that's why the number of elements reduced. The number of pressure vessels, according to this equation, are the same. After correction, we have 36 elements as the same with the previous element. Now I want to simulate it with the software. As you can see, our condition has not changed. We have two stages. In the first stage, we have 4 pressure vessels with 6 elements. In the second stage, we have 2 pressure vessels with 6 elements. But I want to remove the pumps for both stages. And I just change the element with LE400 and get the report. Now, as you can see, in this report we have 2 warnings. First, maximum recommended element permeate flow rate has been exceeded. Please change your system design to reduce the element permeate flow. It means that the LE400 element has a limitation in permeate flow with 5 gallon per minute. As you can see, for the stage 1, we have 5.12 permeate flow gallon per minute. Now we have to reduce it. The second error is maximum element recovery has been exceeded. Please change your system design to reduce the element recoveries. It means that the LE400 element has a limitation for the recovery with 15%. And as you can see, the recovery for the last element in the first stage is 0.17. And we have to reduce the recovery for the first stage. Now I get back to the software to solve these problems. To solve the warning design, I want to apply a back pressure for the permeate site for the first stage. For this, I input 7 psi, and you can see a back pressure created in the permeate side for the first stage. Now I get a report. In the report, as you can see, the first warning that was related to the permeate flow rate solved. But we have still the second problem related to the recovery, and for this I apply again a booster pump for the second stage to solve this problem. I also input a booster pump in 10 psi for the second stage and get a report. Now as you can see, the design warning solved and we don't have any warning in this simulation, and the recovery and permeate flow also reduced in the first and second stages. But the very important point that has to be considered in this design is that if you look at the feed pressure, you can see the feed pressure for this element is 110 psi. For the previous element BW30 was 162. It means that if we use the BW30 element, we need more energy and it's not cost effective. As all our conditions are the same pressure vessels, the same elements, 36 elements, 4 pressure vessels in the first stage, 2 pressure vessels in the second stage, 6 elements in each pressure vessel. With the same condition, you can see affordable element for this design is LE400 that can reduce the cost. Now you can save the project and finish. In the cost analysis page, also there are some notes that you have to know. The yellow cells are the cells that you can enter the numbers such as project life, interest rate, power cost, and so on. The cells with gray colors are the cells that the software will enter these numbers such as unit server, economic evaluation, system water production, system recovery, and so on. And the cells with white color can be calculated with the software. Now we finish this lecture. In the next lecture, we continue designing a ROSA system for seawater desalination using this software. Thank you for your attention.